we're continuing and finishing chapter 6 today, which basically means that we're getting closer to the end of the course. We have only one chapter left. And actually that will be the most important chapter of the whole course. And many of the final exercises, the second homework, will be based on these last two chapters. So please pay attention. Yeah, so let's recall what we were discussing. So we were talking about isolated singularities. Of functions. So we had G, a domain in complex numbers, and A is a point in the domain, and then there was F, which was holomorphic in the domain outside this point. And then we classified three types of behavior at A for F. So first, F extends to a function which is holomorphic in the whole G. So this is called a removable singularity. Second, F does not, but basically there is a power n such that z minus a to the power n times f extends to a holomorphic function of the whole G. In this case, so this is called a pole. And then everything else essential singularity. So suppose F has a pole. So this is the motivation for what I'll be talking about next. So let's consider F having a pole of order n at A. Yeah, it's holomorphic in G without A. So so we choose a disk AR inside G, disk in which G of Z, which is Z minus n minus a to the n f of Z, which is holomorphic in G, has power extension. So we write G of Z as some, let's say, C K Z minus A to the K. K equals 0 to infinity. In a way, I'd like to put tilde here because what I'll write further will be expansion for F. So then of z becomes a sum from k equal minus n to infinity, c tilde, so there's a shift, k plus n, z minus a to the k. Right, it should start from, so the first one appearing here will be k equal minus n, and first c tilde will be c tilde 0. So, right? So we can, so just shifting notation, so shifting enumeration of c tildes, put c k to be equal to c tilde k plus n, k greater or equal minus n. So then we get that f of z is sum of series which I will rewrite as a different sum. Actually, it will be two big summands. So first summand will be sum from k equal minus n to minus 1, ck z minus a to the k. Or I won't even write again, I'll just change notations. I'll write here from k equal 1 to n, c minus k, z minus a to minus k. It's the same sum. So now, plus the usual expansion, k greater equal to 0, k equals 0 to infinity, c k, z minus a to the k. So notice that here the exponents are all negative, and this part has positive exponents. Yeah, and we called this part the inner part, and this part the outer part, or external, internal and external. Also, this was called polar part of. It's a finite sum, so it's a well-defined function. And certainly this part is holomorphic inside this, inside G. Anyways, this was a motivation because what we'll study today is generalization of this, and the title for today is Laurent series. So generalization. So in a way, you see this summation after this change of indices is more general than Taylor series. This is Taylor series, but this is something else. This is polynomial in z minus a inverse. So maybe I should write this explicitly before I pass to general to more general case. So fi is polynomial in 1 z minus a, and fe, external part, is usual Taylor series. In z minus a. Okay, now generalization. Let's start from the definition. So for a sequence C k. K goes from minus infinity to infinity, so all integer numbers. Lorentz series in Z is the following expression. It should be treated formally. It's just a way to remember all coefficients. So as you see, remark, every power series is Lorentz series. In Z is Lorentz series. Moreover, every power series in 1 over Z is also Lorentz series, because we can just stop above 0. So these are like formal observations before we actually start proper discussion. So what can you do with Lorentz series? You can take sum of two Lorentz series. Say dk, z dk. Can multiply by constant. What you cannot do is you cannot take product. Unlike usual power series. So for power series, like for polynomials, we can take product of two power series. It will be another power series. So Lorentz series cannot be multiplied. Cannot take product of two Lorentz series. So also the previous example shows that if a function f has a isolated singularity of A and actually has a pole, nth order pole, at z equals A, then there exists a canonical Lorentz series in the variable z minus A. So of course you can take Lorentz series not only in the variable z but in z minus A. So there's not a big generalization. We'll find from any terms ck not equal to 0 for k less than 0. So this is this series. So you can. Good. Now we want to make sense of convergence. So go. We want to relate general Lorentz series to functions, to homomorphic functions. So in particular, want to make them converge. So that's how you do it. So first of all, you can write the series. So it's just a formal series. A equal minus infinity to infinity ck z to the k. And as we did here, decompose it into two sums. K equal minus 1 to maybe minus infinity to minus 1. Ck z to the k plus sum k equal 0 to infinity ck z to the k. Now the idea is that each bracket here is treated separately. So this is a bracket which is power series. So we can talk about convergence about this power series in Z. Now rewriting this just a bit, we write this as k equal 1 to infinity c minus k z to minus k. I just changed the parameter of indexing. Plus sum k equals 0 to infinity ck z to the k. So we have two series now, and as over there, we treat this as series in z, so in 1 over z. I mean, I can write this as 1 over z to the k. And I can treat this as series in Z. So as such, they have all the features of usual power series. Namely, we can study radius of convergence. Study radius of convergence of the first is summoned in, so the first summoned in 1 over z, and of the second summoned in z. So so let's say that first one converges absolutely for absolute value of 1 over z less than rho 1. And second sum converges absolutely for z, absolute value of z less than rho 2. Then this is equivalent to saying that z by absolute value is greater than 1 over rho 1 if rho 1 is not 0. So now we see that in principle, if 1 over rho 1 is less than rho 2, then we can study convergence of both together. So absolute convergence of 1 and 2 together. Well, it's a condition on series. So of course there are series where this is not satisfied. Then we cannot talk about convergence. But we impose this condition. So then the area of convergence becomes the area of mutual convergence of both 1 and 2 of absolute convergence of both 1 and 2 is 1 over rho 1 less than absolute value of z less than rho 2. So if we draw what this means, then we have two disks So one of radius 1 over rho 1, and the other one with radius rho 2. And our z belongs to this area, which certainly should be called a ring between rho 1 over rho 1 and rho 2. But since we are following French tradition and they were following Latin tradition, a ring in French is anneau, and it comes from Latin, so the word used in the book is annus. So A of 0, this is the center, 1 over rho 1, and then rho 2, this is Z, 1 over rho 1 less the absolute value of Z, less than rho 2. This is open annulus with the center at 0 between these right. So some of these we already met. Let me remark that if rho 1 is infinity, then 1 over rho 1 of course is 0. So then annulus around 0 with parameters 0 and let's say rho 2. So we basically throw away the point 0. So this is simply what we earlier called k prime of 0 rho 2. So it's Punch's disk around 0. Yeah. So if rho 2 is infinity, then basically this A0 1 over rho 1 infinity is simply C minus the closure of. So it's just complement to this. But the most general shape we're interested in is this annulus. So from now on we will not write 1 over rho 1. So from now on we'll work with annulus. So from now on work with annulus around the point 0 with radius R1 and R2, and more generally if we want to study Laurent series in Z minus A, A of some point A, rho 1 and rho 2, which is Z absolute value of Z minus A being between R1 and R2. Okay, so now we're in a way change the area, the typical area where holomorphic functions now are presented by series. All the series become Laurent series instead of power series. So now, just in the same way as we did it for when we did this Cauchy business, we want to present any remark given a holomorphic function in some annulus, want to present it as a sum of Laurent series. in z minus a. So it's important when we study this that this point and the area, so this annulus we're studying, are part of the data. So we'll see there'll be, in the end of the lecture, there'll be a big example which shows that it's not only about the point, it's also about the region, so this annulus in which we're finding the decomposition. So there'll be an example where different annuli at the same center for the same function given by the same, rational expression produce different Laurent series. So it's important. Exactly because convergence we study depends on this annulus. Okay. So here is the main theorem. And then we will slowly prove it. So suppose we have some function as I said. So for every such function, so there exists unique Laurent series converging to f absolutely. And coefficients are given exactly by the same expressions, for Taylor series and the case when R1 just didn't exist. So coefficients Cn are given by the formula similar to Cauchy integral. Only now n belongs to z. So pay attention. See, sometimes this denominator, so for negative n's, it becomes numerator, in fact. So instead of dividing, we start to multiply. And then we'll start to get Cn's with negative indices n. But the formula itself is exactly like in Cauchy integral formula for derivatives. Right? So. Good, so where, I didn't explain what R is, so where it's just any radius in between. So let me redraw this picture. So we have the annulus, where so it's centered at A, and then we start integrating by any circle inside. So this is R1, this is R2, and this is small r. Good. So let's prove this. So first, proof. Just let's see that this integral to any power, so n is z, does not depend on a choice of R in the area we're allowed to choose it, and the proof is absolutely clear and easy. So we have indeed, so it's the usual consideration with these integration curves. So this is like R2, the bigger one. This is R1, the smaller one. We make a cut, and then we so we can go like this. Okay. So and like this, like this, like this, then like this, and ending at the point. So we will see from this that we can integrate over this closed curve. I drew it, so I start from this point, I go up, I go around, I come back. So I'll call it gamma. So the integral of gamma of f of z, z minus a 2 n plus 1 dz. Certainly it's 0 because, well, we used it, you used it in a wonderful way in this solution, at least I like, of problem 4 in the exercise. So we have a closed path, and it's contractible and whatever. So then holomorphic functions do not have a non-zero integral there, and the function is holomorphic inside. So anyways, since we have this, we decompose the integral over gamma, and then we'll see that it will be integral over gamma. I won't even write of what. It will be sum of integral over dk of a R2 of the same thing, plus, call it L, for example, integral over L of something, plus integral of minus L, because we return, of something, and then plus, finally, integral, but the direction is opposite, so minus dk of a R1 of the same thing, and in total it's 0. So these two cancel out, and we get that, let me write it in the corner, that the integral over dk a R1 of f of z, z minus a to any power, equals to the same for R2. There will be more pictures like this in the proof. Great. So then, indeed, it's independent. The remark is proved. Now, let's assume that f is already sum of Laurent series. Suppose f of z already is realized as sum from a equal minus infinity to infinity ck z minus a to the k. So absolutely converging, blah, 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 blah. And we want to see, so we want to see that ck indeed equals as written. Let's prove this. So just substitute. So indeed, we write 1 over 2 pi I integral over dk of a r f of z minus a to a plus 1 z, and then we substitute this series expression. Let me put n here, just to distinguish from summation. So then we substitute the sum. K equals minus infinity to infinity. So let me write it as ck and then z minus a. With this shift, we'll get k minus n minus 1, because we have this denominator, and then dz. And then we have the circle, which is compact, and yet, so this convergence is not only absolute convergence, but uniform and compact. So series converge uniformly on compact, and our our curve of integration is compact. So this is the standard trick in this story. So we can rewrite integral of sum as sum of integral, and let's see what we get. So we can treat every summand separately. So let's see. So I just continue the summation. I continue the equality. 1 over 2 pi I. Sum for k goes from minus infinity to infinity. And now integral over dk ar of so c k stands here, and here we have dz times z minus a k minus n minus 1. So we know it's a direct calculation, and also it follows from existence of primitive so all of these z minus a to some power s, or 1 over z minus a to the s are derivatives of something, with the one exception, which is 1 over z minus a. So then this integral vanishes almost always. So n here is fixed, but k is a parameter of summation. So almost all these integrals vanish, with one exception, when k minus n minus 1 equals minus 1. So all summands die. So r equal to 0. Okay. Acquired, no. The one with k a minus n minus 1 equal minus 1. So k equal to n. And the 1 equal to n becomes integral of 1 over z minus a over this dz, and we know that this simply equals to 1. So then the total thing becomes, so I can continue this equality. So it becomes simply Cn. So the only non-vanishing summand is Cn times 1. So let's see where we started and where we ended. So we get that get this for f given as sum of series. Good. So this was the easy part. The difficult part is to prove existence of such presentation for a given holomorphic function. And that's what we'll do after the break.